Hello, my name is Tom Marsh from the University of Warwick in the United Kingdom, and I'm going to be talking about high-speed astronomy. That is, objects in the sky that vary fast, how we observe them, and how we learn about them. I hope you enjoy it. To begin with, I'm going to show you some data along with the brightness extracted from them, just one example of many. So what you see here on the left hand side is the actual images taken in a sort of movie mode here. Just a star, you're not seeing anything else in the field, which varies quite dramatically. This is a very unusual object and we'll talk about it later. We measure these in devices called CCDs, charge coupled devices, and what you're seeing here is just the number of pixels along the X and Y axes. It appears to be moving, the object appears to be moving, shaking, but that's actually the telescope shaking. The object is just fixed on the sky and the telescope itself is being blown by wind all the time. But if you look at the object, you can sort of see that sometimes it gets distinctly brighter, and on the right hand panel you're actually seeing the brightness extracted from this data. And look at the scale in minutes along the bottom, going up to 60 minutes, and in this case you're seeing very strong pulses from this object every 2 minutes. That scale starts at 0 at the bottom, and so sometimes it's getting 3-4 times brighter in just tens of seconds. This is an extremely variable object, but it's just one of many thousands of variable objects in the sky. Very often they're not obvious to us by eye, and you have to measure it in this sort of way to actually see it. I'll let that run. This particular object is just varying like this all the time. Every point there is another exposure, and this is being observed every few seconds in this particular case. And this is a very typical example of high-speed astronomy. So moving on, look at my talk outline here. So I'm going to first talk about astrophysical timescales. What can high-speed observations actually tell us? Then, once I've gone through that, I'm going to look at a few case studies just to show you examples of how high-speed observations can be useful to understand particular objects. We'll look at 3 particular objects, and we'll come back to these later. But it turns out we can study whether there are planets, things called gravitational waves, and finally a very unusual source called AL-SCO, which is powered by relativistic effects. Apologies if you hear some noise on the thing. I'm going to try to prevent that. Right, apologies for that. So first of all, I'm going to talk about what I call astrophysical timescales. There are particular timescales that are important in astronomy. I'm going to first start off with the shortest one of all. So no object can be seen to vary in astronomy except under exceptional circumstances on a timescale shorter than it takes light to go across it. Okay, so if you have a particular size, which I call r here, then just r divided by the speed of light, c, gives you the sort of time scale on which you can expect ever to see it vary at the very shortest. Very often it won't vary on that sort of time scale. Just an obvious example, it's not really very practical, but the nearby galaxy M31, which is one of the nearby galaxies to the Milky Way, somewhat larger than the Milky Way, 200,000 light years across. If all the stars in M31 went out simultaneously, well, you wouldn't see that happen for around 200,000 years, because that's how long it takes the light to get from the furthest side relative to the nearest side. So it would gradually go out. The nearest stars would go out earliest, and then the most distant ones would go out at the end. And that's what I mean by the light crossing time. It sets a very fundamental limit to the typical variability of most sources. And there's only very unusual cases where you can exceed that. M31, 200,000 years, we're not going to see that, but for much smaller objects, then these timescales can come into the human range. And so think about the Sun. It's got a size of 700,000 kilometers. And if it suddenly stopped shining simultaneously at all points on its surface, we wouldn't see it go out instantly. It would take a little bit of time. In fact, it would take about 2.3 seconds for it to disappear. We would see the light disappear first at the center of the Sun's disk, because that's the part of the Sun that's closest to us, and it's at half a second it would look something like the second image here, as I indicate, and then at 1 second most of the Sun would have disappeared, but still we'd see that very edge part just for another second or so, and then 2.3 seconds we'd see it no more. That's nothing to do with the Sun, it's just to do with how long it takes light to travel across the Sun. And there are three types of what we call compact stellar remnants, very small remnants of stars that give much shorter times still because they are so small. So the most common remnant of stellar evolution are called white dwarfs. They're about the size of the Earth, radius of 6,000 kilometers, a light crossing time of 20 milliseconds. So that's the shortest possible time a white dwarf could vary on. And then much smaller than that are neutron stars, the size of a city, 10 kilometers radius, and the light crossing time there is 30 microseconds. And then we have black holes, which can be comparable to neutron stars at their smallest, but they can also be larger. These are stellar scale black holes I'm talking about. The light crossing time there is anything from the same as a neutron star, 30 microseconds, to a millisecond. Very, very fast, potential variations from these sort of systems. Now the light crossing time is the absolutely shortest possible time in which variations can be expected, but very often a more important time scale is what we call the dynamical time scale, and that's related to the orbital time for an object, which is essentially how quickly gravitational equilibrium can be restored. If you could perturb the Sun, this is the sort of time scale on which it could re-establish equilibrium. The dynamical time scale of an object of mass m and radius r is given by the formula here. Square root r cubed divided by gm, where g is Newton's gravitational constant, and rho here is the density of the object, or more correctly the mean density of the object. Okay, so as soon as you can measure time scale of an object, you very often get an idea of its mean density, which can be extremely useful just immediately as to constraining the sort of star that it might be, for example. So here are some dynamical timescales I've calculated here. So for the Sun, 1 solar mass, 1 solar radius, it's around 26 minutes. For white dwarfs it's around a couple of seconds, 2.7 seconds. White dwarfs are very small. But neutron stars, it's down into the microseconds. So in the case of neutron stars and black holes, the dynamical timescale is actually comparable to the light crossing timescale, because the orbital speeds around those objects are comparable to the speed of light. So they're very, very short. So you can get variability down to these sort of timescales. So these are very, very important constraints on any object, just from very simple observations. Okay, so that's just the background on astrophysical timescales, and it's important to keep that in mind as we go through some of the cases. And we'll see some cases where you can exceed these sort of dynamical timescales for other reasons like eclipses and things like that. But they are very, very useful reference numbers. Okay, so I'm going to now go on to what can high-speed observations tell us. So I'm going to start off with another movie, and we're going to see some observations taken from the TNT, the Thai National Telescope at Doi Inthanon, in 2021. So again, I'm going to be showing images of the sky on the left-hand side and the actual brightness extracted from the images on the right-hand side. So look carefully on the left-hand images because you'll see one of the stars disappear. So watch carefully. So this is a star that most of the time is very constant, but then it disappears and it will reappear soon, so look out. And once it comes out, it's constant again. So note how this is an eclipse of a white dwarf. This white dwarf is the size of the Earth, but it's being eclipsed in this case by an unseen companion object that's much bigger than it is. It's more or less 10 times bigger than the white dwarf in this case. And when it goes in front of it, it completely obscures it. And the white dwarf is by far the brightest of those two stars. And so when it is eclipsed by its companion, you just can't see any light at all. It goes down to zero, as you can see down at the bottom here. But before it's eclipsed and after it's eclipsed, you're just seeing the same constant level of light. It's not varying for any other reason apart from the eclipses in this particular case. You can see how fast it takes, and that's just related to the size of the white dwarf and the speed of the star going in front of it. I'll run it once more time just in case you missed it. It's this object here. Have a look at it and you'll just see it disappear, concentrate. This is a bit speeded up compared to real time. This whole thing takes around 12 minutes in eclipse, not just a few tens of seconds. Nevertheless, it's a fast variation. So from those sort of observations, you can build a picture of the object. I was talking about the unseen companion and how it went in front of the white dwarf. And you can make measurements. You can measure numbers. You can measure sizes and things like the geometrical orientation of the object. And so this, on the left-hand side, is just an illustration of the sort of object we were actually looking at that point. Very, very bright, hot white dwarf, and some very dim, reddish, as cool companion here. In this case, you can see it, but as you saw in the previous video, you couldn't even actually detect any flux from it in reality. Very dark on its back face, or it's heated on the front face near the white dwarf. But these sort of objects are quite plentiful. There are, we know, hundreds and hundreds of these where we see eclipses. And we can use those to measure the sizes of the white dwarf, and with other measurements we can measure the masses of the white dwarf, and that allows us to test theory, because astrophysical models of stars are able to tell you what their radius should be for their mass through understanding their physical composition and the physics of their interiors, and those are called stellar structure models. And so we have theory and we can directly test it with observation. And that's exactly what I've got on the right hand side. I've got a series of measurements of radii on the vertical axis and mass on the horizontal axis of a set of these white dwarf stars compared. The lines here are various models. It's a little bit complicated to explain the details. It depends on how hot the objects are and effects like that. But essentially, these observations are in very good agreement with the theory, and we can test some of the details of the theory. For example, whether the white dwarfs have got layers of hydrogen or not makes a difference to how big they are. and it's these sort of very precise high-speed observations that allows us to do that. A little bit more detail on that. So this is the same eclipsing white dwarf, but I've just shown you the brightness here as a function of time covering an entire orbit. So this particular system takes about 3 hours to complete an orbit. They're very, very close to each other. And so at this point here, you're seeing the white dwarf being eclipsed. Then you see this rise in flux, and that occurs as you see the heated face of the star. So if I go back one, you remember in this artist's impression, you can see it's so brighter on this side of the cool companion. That's because it's being heated by radiation from the white dwarf. Okay, so when we see that fully pointing towards us, we'll see it looking much brighter than when we are looking just at the unheated side of the star. And that's what we see here. So essentially around here we're seeing the unheated face of the star, which is almost nothing. We can't really detect it. But as we start to see the heated face of the companion coming into view, then we get this very characteristic rise, sometimes called what's called the reflection effect. And if I then zoom in this region here, just around that time there, that's when the white dwarf is going in front of the face of the heated face of the companion. And if we're lucky, we can see a very, very small dip in the flux due to that white dwarf, and that's exactly what we're seeing here. Okay, so this is the very peak of the light curve, and at this point here we're actually seeing this. By the way, this is you can see the numbers are slightly different because this is a redder filter, but otherwise it's the same effect. We're seeing a little dip around here and a little deficit in the flux as the white dwarf passes in front of the face of the companion. And so these are the sorts of data from which you can get very precise numbers, as I showed in that earlier plot. Okay, so moving on, let's look at a different aspect. We can look into the hearts of stars with high-speed observations through pulsations. So stars ring like bells, effectively. They have many ways in which they can oscillate, just like a bell does. A bell has multiple frequencies. Well, you can't hear them very easily, but it does have multiple frequencies, and so do stars. And sometimes they can be found to be oscillating in those frequencies. And you can see that through minute changes in their flux. And this shows an example where you can see what you might call beating, where there are more than one frequency present, and sometimes the two frequencies line up and you get a strong pulsation, and then they're slightly different frequencies, so gradually they get out of shift and they start to cancel each other a bit. And so what you're seeing here is large amplitude, small amplitude type variations, and that's how we can look into the hearts of stars through measuring these pulsation frequencies. Another different aspect is that you can detect planets around binary stars through timing with high-speed observations. So here's an example of an eclipse here, and just to show you that they can be very short. This is just 2 minutes long, and I can run a model through the data, which I can say is positioned correctly to really very, very precise values, much less than 2 minutes, in fact less than seconds in some cases. So I'm able to say when the eclipse happens to second or sub-second precision. Why is that useful? Well, just imagine here that I have a binary here as shown with the blue and the red dot here. This is the binary as it appears to us at the time of mid-eclipse, and over here is us looking at the system, and at this point here it's time to be the eclipse, and we can measure that and measure the time. And then here is the same binary again, but some other time later, if it's orbited in a much longer orbit by some sort of unseen object, in other words a planet. So a planet is able to perturb the position of the binary slightly. And so at this point here it's actually closer to us, and so we'll see the eclipse coming a little bit earlier. than it would do otherwise. This point here, it's a little bit away from us, and we see the eclipse a little bit later. And so we can expect to see some little wobbles in the eclipse times from a system like this if it's got planets orbiting it. So it's an indirect way of detecting planets around close binary stars of this sort. I'll show you an example later. Here's another use of high-speed observations, different from all the others. It's what are called solar system occultations. So, for example, if a moon of a planet or a planet itself or an asteroid passes in front of a background star, and you can measure the flux variations, you can get very exquisite constraints upon the size of the moon, planet, asteroid, and exactly how it's moving. So these are called occultations, and they can reveal very interesting detail of atmospheres. If an object has an atmosphere, it won't just block the light immediately, you'll see it fade. And also if something's got a ring around it, rings of Saturn, for example, when they pass across a background star, you'll see dips in the light curve that allows you to measure the rings very precisely, and in ways that you can only match by going there directly with an expensive space mission. Just a little bit on the physics. I don't expect you to understand this, but it's quite complicated. It's to do with the diffraction of light. But the shortest observable scale you can measure, the very smallest size, is set by something called the Fresnel scale, and the Fresnel size is equal to the square root of the distance to the object, distance to the asteroid or the planet, times the wavelength you're observing at. And that sets the size. So if you consider something that's in the outer solar system, it's at 30 astronomical units, and you observe at a optical wavelength 500 nanometers, okay, you can work out this time scale. And if you remember that the Earth itself is moving at 30 kilometers per second, and we're moving through the shadow essentially, then we can sort of see the time scale on which we could get variations. You can work that out quite easily. I encourage you to do that. You find out a time scale of around a 20th of a second, really fast variations. You need to actually see these sort of effects at the full detail. Can't always go that fast, but that's what you would if you were really trying to resolve them. And here's a beautiful example of this. Really lovely discovery, completely unexpected because it's the only one so far known. There's a minor planet called Chiriclo. You can sort of see the scale here, 100 kilometers. So we're talking something really small, asteroid size object. And it turned out it was observed, it was predicted that it was going to pass in front of a background star, so people were ready to observe it, to measure it going across that background star, because they were interested in trying to work out the shape of the minor planet by these observations. So they had to observe it at multiple different places. These are the names here are all the observatories on Earth that they were looking at it with. But when they did this, they suddenly discovered two little dips before and after that you interpret as a pair of very narrow rings around that object. So that was completely unexpected, and you can't see it directly from Earth. You can only see it here because it's obscuring the light. But you can just see, so this, look at the time scale here, 23,120, that's in seconds, 23,140. So we've got 20 seconds here in which we could see this sort of variation. Each point here is a point within that discovery. These data are taken from Chile, La Silla, and you can sort of see the path it made across the rings and the satellite here. And that led to a Nature paper from just 20 seconds of data. Beautiful observation. Okay, so that's what timing can tell us, and now I want to move on to some case studies. So looking at 3 specific examples where we can I've already looked at some of the data from those, but looking in detail at some of the aspects that I've just talked about. So I'm going to start off with a star called NN Sur, which I showed you the light curve of when I was talking about the size of white dwarfs. But we're going to look at that in a bit more detail to try to look for planets around that system. Then I'm going to talk about some long, what we call telephone number, ZTFJ 1539 plus 5027. This is a beautiful 7-minute orbital period, very, very fast binary, and what's called a gravitational wave source. So I'll tell you a little bit about that. And then finally, I'm going to go back to that star I started off with, the one with lots of pulses, and talk a little bit about that and what we think is going on there. So this is one we've seen before. This is the eclipse of a white dwarf. So from here to here is 12 minutes, and these sort of the eclipses, this is what we call the ingress, and this is the egress of the eclipse. That's basically fixed by the size of the white dwarf, and it's taking about 40-50 seconds to be eclipsed in this particular system. But you can see it's very sharp, and I can run an accurate model through the data. Now I'm very sensitive to exactly when the eclipse happens. I can't move that model very far without disagreeing with the data. So why is that interesting? Well, I talked about how you can pick up a unseen planet around such a system, and so the question is, well, how accurate do I have to be to actually see that? So a good comparison is Jupiter and the Sun. And if you work it out, Jupiter is 1,000 times less massive than the Sun, and that means that it moves the Sun about 1,000th of its own orbit around the Sun in terms of distance as it orbits on its 11-year orbit. So, and if you then divide that by the speed of light, you get the amount that the Sun is moving back and forth, if relative to other stars, for example. And Jupiter moves the Sun back and forth by around 2 light seconds. That's the distance not light years, but light seconds during its 11-year orbit. So if the Sun was varying in such a way that I could measure it accurately, I would be able to see that very small variation, 2 seconds back and forth on this 11-year cycle, and I would be able to say that Jupiter's there. Now, the Sun doesn't, but a binary like NN Serpentis, this one here, does. So its sharp eclipses can be timed to less than 0.1 seconds, and so I could quite easily pick up something like Jupiter if it was orbiting around NN Serpentis. And in fact, we could see something quite a lot less massive than Jupiter. So what do we actually see? So this shows 28 years, long times. This started around 1990. It's up to 2018 or so, of measurements of these eclipse times. Okay, so we expect them to come regularly every 3.1 hours if there was no planet, but if there is a planet orbiting it, they will wobble back and forth by a small amount because of that planet. And so what I'm showing here is what's often called O-C, observed minus calculated time, which is the measured eclipse time minus a calculated time assuming just regular eclipses every 3.1 hours with no planets. But you can see that it's not. If there were no planets, it would be completely straight, but it isn't. It wobbles up and down relative to that. And what I plot through there are models assuming that the system is perturbed by planets, by 2 planets, in fact. And you can fit it. The fit goes through if you have 2 planets of around 2.5 and 7.5 times the mass of Jupiter. So a nice indirect potential way of detecting planets. And this artist's impression here is sort of meant to show the system itself with its white dwarf and its cool star. The cool star happens to be similar in size. It's meant to be seen further away here. 2 potential planets. So you need 2 distant planets to produce these variations. The next case study I'm looking at is the gravitational wave source. ZTF comes from a particular survey in California, J1539 plus 5027. You often see these sort of names, by the way, in astronomy, and they're basically referring to the position on the sky. It's like a longitude on Earth and a latitude on Earth. It's just telling you where the object is. Sometimes you also see names like NN Sur, but there are so many interesting targets nowadays that you'll tend to see these number type names more often, and often you'll be even longer than this. So this source is what I call a gravitational wave siren. It's the shortest period eclipsing white dwarf system known, and it's slightly less than 7 minutes. And so I'm going to show you another movie, and the movie will show you the system in the same way as before. I'll show an image of the sky and also the brightness of the object. So again, look out and see if you can see the variable object. It should be fairly obvious. And then just we'll talk a little bit about the brightness that results from it. So on the left-hand side this is a very faint object. The left-hand side is the field. You can see various stars in there. Those are just random stars nearby. And just look every so often, you'll see something disappear quite rapidly. And I hope you'll see around here that object there blinking on and off. Also look that although you can see it vary dramatically during the eclipse, it also varies outside the eclipse, but that's not nearly so obvious. It's not always easy when you're looking at the raw data to see this sort of effect. And that's because there are observational effects. As I'm observing an object like this, the width of these objects can vary because they're being blurred by the atmosphere. Maybe the telescope moves a little bit. So everything looks as though it's varying when it's not necessarily varying very much. I'll have one more look just to look in a bit more detail. So if you look, and you'll also see the whole thing seems to flicker if you look at the left-hand side, and that's due to random noise. It's a very faint object. This one is observed on a very large telescope. So have a look at some of the brighter objects. So they are actually totally constant, but they don't look it necessarily. And it's only by extracting the data that you can actually get the data on the right-hand side, which shows you the actual brightness. So what we're seeing there again is the eclipse of the hotter component is the dominant drop down, but again we're seeing that it's heating its companion component, and this heating of the companion is giving us this rise and flux between the eclipses. And it's also, there's a clear effect where the hotter star is going in front of the heated face of the companion and obscuring it a little bit. It's rather more obvious than in SIR in that sense, and that's because the two stars are more equal in radii in this particular system. So it's interesting. This system has it's really very fast. You can see I've just got half an hour of data here, and it's already got 1, 2, 3, 4, 5 eclipses, and its orbital period is 7 minutes. So during this talk it will have completed 7 orbits, and this is an interesting star because it's quite extreme. And the reason why it's interesting is that not only can we see it directly, but we are almost certainly going to be able to see this through gravitational waves. There's a space-based mission called LISA, Laser Interferometer Space Antenna, that's due for launch in the 2030s, and this particular star will be one of the first sources that can be detected with this, that we know of at the moment. It will be detectable within a few days by LISA. If LISA works, it's going to actually be a useful source to calibrate it. The idea of LISA is detecting gravitational waves, which are small perturbations of space-time, and it does this by measuring the distance between 3 satellites, or actually an object inside each satellite, using laser interferometry. It's going to have arm lengths from here to here. It's going to be 2.5 million kilometers. And over that scale it's going to be detecting changes in length of less than an atom in diameter. Those are very, very weak perturbations from gravitational waves. But nevertheless, this particular star will be strong and should be detectable quite fast. And now, interestingly, we can actually use the high-speed observations on the ground to already predict some of the properties. So one of the things we can do, we can measure these eclipses again, these eclipse times, and we can plot them as how they change relative to no change, no orbital period change at all. And what we see is that these eclipses are getting earlier and earlier with time. Okay, so from the period at the start, if they hadn't changed period, there'd just be all these points would be along here. But we now find that they're coming, tens of minutes earlier than we would have expected otherwise. And that is the effect of gravitational waves, which are actually causing the two stars to spiral together faster and faster. It's quite a slow time scale, but on an astronomical time scale, that it's going to be very short. These two stars are going to be merging with each other in 200,000 years from now, which is tiny compared to the age of the universe. And so we're already seeing that, and that's what LISA is designed to pick up directly in the gravitational waves. And so this shows on the right-hand side is the strength of the gravitational wave strain it's called, and that's the sort of relative perturbation in length that it causes as a function of the frequency that we see it. And LISA, the line here is the detection threshold for LISA, and these are some of the sources that we already know about, or we're expecting many thousands more. These are some of the sources we already know of, and this is where ZTF 1539 plus 5027 is to be found. It's one of the strongest and shortest period sources, and it's also one of the ones best known, so we can really say that it's almost got to be exactly around here, and so it's very, very useful source for testing LISA. And you can see that relative to the detection threshold, it's almost a factor of 100 above that. So it's a very high, what we call signal to noise source from that point of view. Okay, so the final case study I have is going back to the very first object that I talked about, AR-SCO it's called. So it's got one of these name type objects, names rather than numbers. And let me show you again that light curve that I showed at the start. So once more, on the left hand side is a picture of the image, and in this case I've just zoomed in onto AR-SCO itself because I want to show you some of these observational features of shaking, and sometimes you might see it get a little bit blurrier, the image, not so obvious, or it sometimes jumps, and that's what happens during observations. That's all due to the Earth's atmosphere and the telescope. It's not due to the star, but the star in this case, as I showed before, is definitely varying quite dramatically. It's got a pulse every 2 minutes here, and some that you can also see a very strong pulse every 2 minutes, and in between those is another little pulse you'll see as well. So they're coming every minute, and so sometimes you're just seeing these huge rises in flux, factors of several within just tens of seconds. Our model for this, which I'll be talking about a bit more, is that we're seeing a sort of lighthouse. It's a spinning white dwarf that's flashing radiation towards us every 2 minutes, a bit like a pulsar, but it's a white dwarf version of a pulsar. The observations of this system through high-speed observations we're pretty sure of what the nature of this particular object is. It's not just a white dwarf; it also has a companion, and you can see the sort of general rise in flux that's happening here is associated with the orbit of the companion. So let me let that run through. It's quite erratic, this source. You don't always know how strong these pulses are going to be. Remember, each one of those points is a separate image. Okay, and then I'll just talk a little bit about this object, how we found it, how we sort of learned about it. So AR-SCO, or it's object in Scorpius, so it's called AR-Scorpii. AR means that you see the two letters. It means it's a variable source. It was known to be a variable source many years ago, more than 100 years ago, but it was misclassified. We didn't understand what it was, and then it was recognized around 2015. A group of amateur astronomers, it's quite a bright object, observed it, and they found this light curve that they couldn't really understand. When I say a light curve, I mean a flux versus time. And they could see that it had a very obvious period, a 3.56 hour period. That's the orbital period. But the really peculiar thing is it varies by a large amount. So this is in magnitudes, and you have to understand the magnitude scale. But from the minimum, this is the faintest and this is the brightest. That's more than a factor of 4 brighter, and that's actually very difficult to understand. There are some objects that look like this, but they can't vary by that much, and so it immediately became obvious that there was something funny about AR-SCO. And also, if you look around here, sometimes you're seeing it's really bright, but other times it's quite faint. And it's not obvious on this plot, but that's due to the pulsations, and so these were the observations that indicated there was something funny about this object. We then went and looked at it with the high-speed cameras, and in fact the very first observation we got was this one here. This is taken from a telescope called the William Herschel telescope. It's a 4-meter telescope where they had a high-speed camera, and these were our first sort of observations. We saw these really dramatic pulses, and we could see there was something very odd within the first 5 minutes because these pulses were so odd. But then we got more observations at different wavelengths, and this is one of the very peculiar things about this source. It pulses like this in all the wavelengths we've ever observed it at, not by the same strength necessarily. So the strongest ones are here in the ultraviolet. This is with the Hubble Space Telescope. And you're seeing these very strong pulsations. Some of these are by more than a factor of 100 from minimum to maximum, within 30 seconds. So it's really quite a dramatic change in brightness. When you go towards the redder, longer wavelengths, the pulse is still there. They're not quite as strong, but most peculiarly, you can still see them in the radio and detect it in the radio. And normally these sort of objects are just not very bright at all at radio wavelengths, so just seeing it in radio is very unusual. And so this led to our sort of current picture for this particular star, which I'll be talking about. So we've done further observations since, and we can measure these 2-minute pulses quite accurately again, and we can do the same sort of trick that we did for the relativistic source, where we measure the times of the pulses over a long time scale. And what we find is that these ones are arriving, the pulses are arriving later. They're slowing down with time. Okay, so contrast that with the gravitational wave source, where the eclipses are arriving earlier and earlier with time. These pulses are arriving later and later with time. So this isn't speeding up, it's slowing down, and this is a spin of a white dwarf, magnetic white dwarf, that's losing energy and gradually slowing down. It's slowing down on a much longer timescale. It's slowing down on a 5 million year timescale. Still short by astronomical standards, but not as short as the gravitational wave source. But they're very different sources. So what we think we're seeing here is magnetic white dwarf spinning on this 2-minute period, and it's the magnetic interaction between the white dwarf and a companion star, the companion that's on the 3.5 hour period. The interaction between their magnetic fields is actually causing acceleration of electrons. So when magnetic fields interact in astronomy, you get having to break the field. The field changes its configuration, and as it changes that, it's almost like an elastic band. It can accelerate particles to high energies, and in this case it's accelerating them to relativistic energies, and it's then those relativistic energy electrons within the magnetic field that are producing the radiation across radio, the infrared, across all the bands, and explain the very unusual nature of this source. So it's a very unique thing that could be revealed through high-speed observations. Where's the source of that energy is the rotational energy of the white dwarf itself. It's losing rotational energy as it slows down, and it's putting some of that energy at least into the radiation that we see. So I hope that rather sort of whistle-stop tour of the high-speed observations and some objects gives you an idea of the sort of things that you can do, and you might not have been aware of how quickly objects in astronomy can change. But so despite their size, astronomical objects can really vary quite fast. There are many millions of variable objects in our galaxy alone, and many other galaxies. And high-speed observations can probe to tiny length scales in astronomical terms. So we can reach out across light years to probe the nature of systems through these sort of observations. And just remember, I hardly even mentioned the very fastest ones of all, neutron stars and black holes, where you can see variations at hundreds of hertz, very dramatic variations, which have been measured in the same sort of way, but even faster than that. And these are pushing the limits of what we can do, because these objects are faint, and so it's difficult to get many photons within short time scales. We need big telescopes to do that. So thank you very much. That's where I'll stop here, and I'll also be making a presentation for the associated questions on this topic. Bye bye.